Hello, everyone. My name is Chen-Pei Huang, a PhD student from University of Houston. Today, I'm going to present our work titled Reverberating Stress Wave Channel Capacity in Pipe Communications. Here is today's outline. First, I will introduce the motivation of our work and why we want to use pipe for communication. Then we investigate the reverberating stress wave channel from both simulation and experimental results. In the next section, we calculate the stress wave capacity in two scenarios. The first one is the point-to-point stress wave communication, and the other one is the on-pipe sensor data aggregation. Finally, I will summarize this work, and let's begin with the motivation. The Gulf of Mexico has more than 3,000 active wells and over 43,000 miles of pipelines deployed during the last century. Inadequate monitoring and maintenance of the critical infrastructure may lead to ruinous economy loss and environmental disasters. In 2010, damaged subsea infrastructure leaked more than 200 million gallons of oil into the Gulf. So it is vital to monitor the structure health and send the data from subsea to the surface. The current underwater communication is majorly the underwater acoustic communication. Let's begin with the power spread. For the deep water, there is a spherical spreading, while for the shallow water, there is a cylindrical spreading. Both of them have significant spreading loss. Apart from that, multipass fading, frequency-dependent attenuation, and Doppler shift limits the data rate. The challenge now is focusing on how to develop a more reliable underwater communication technique. Can we use acoustic waves in solid material for communication? The answer is yes. We can use a guided sound wave in metal pipe called stress wave communications. We still look at the spreading loss as an example. In the stress wave communication, the stress wave is guided by the metal pipes, resulting in reduced spreading loss comparing to the underwater acoustic. Furthermore, the velocity of stress wave is twice of underwater acoustic, and it also benefits from the relative smaller attenuation. So, the stress wave communication is quite suitable when the sensors are fixed on the pipe wall. We can use the existing pipeline network to monitor the infrastructure and send information. In the next section, we focus on the channel characteristic. We investigate the stress wave channel from model analysis, simulation, and experiments on the testbed. Let's begin with the system model. This figure illustrates the stress wave communication system. At first, the piezoelectric transducer acts as a transmitter, converts the electric signal into magnetic vibration. Stress waves are then generated and propagate along the metal pipe. Due to the discontinuity of the pipe, it reflects at pipe end and joint. The resulting vibration at the receiver side will be turned back into electrical signal, and this signal can be decoded. Generally, this stress wave communication system consists of two parts. The metal pipe is the medium that stress wave travels in. Propagation is governed by the Navier equation. The cylindrical metal pipe is also a dispersive media, and due to the discontinuity from the joint and end, the pipe also reverberates. And for the transceiver, lead zirconic titanic piezoelectric transducer is selected. It has strong piezoelectric effect, making it a desirable actuator, and it also has a wide bandwidth and cheap in price. We use the console multiphysics to simulate the source vibrate while the stress wave reflects at both two ends of the pipe. And we test the system using sinusoid signals. Here in this figure, we plot the results at some frequencies. We observe that the transmitting at unit power, when frequency changes, the averaging pressure will also change. It also shows a spatial correlation. We also find that the channel response at each fixed point doesn't change over the time. So as a result, we can say the stress wave channel is a time invariant and spatial correlated channel with the frequency-dependent channel response. Next, we build our testbed in the lab with a T-shaped steel pipe. The distribution of the piezoelectric transducer are put along the pipe longitudinal axis, while their coordinates are shown in the bottom figure. We use the chirp signal to sound this channel, and we sweep the frequency response from 100 to 500 kilohertz. This linear frequency modulation starts from a very low frequency to the highest frequency. And the sweeping time we set here is 100 milliseconds. The result is shown in the right panel. The top right figure shows the power spectrum density of a fixed receiver. This figure is derived from the autocorrelation. The frequency response is observed non-flat, and we can see the maximum response is around 200 to 300 kilohertz. We also plot a spectrogram in the bottom figure. Most delay spread is observed smaller than 4 milliseconds. However, at some frequencies marked in the red box, the delay can be up to 10 milliseconds. We then consider the broadband communication. If we use this broadband signal, we can transmit more information. But here is the question. Using this broadband signal in the stress wave channel, it can be significantly distorted due to the dispersion and the reverberation. The OFDM is a powerful tool to combat this non-flat channel by dividing the overall bandwidth into subcarriers, so that each subcarrier will face a flat channel. We list the three advantages using OFDM. The first is its easy implementation. You can use the fast Fourier transform efficiently demodulate informative bits onto subcarriers. And second, the overlapping subcarriers increase the spectral efficiency. Third, intersymbol interference can be eliminated by the cyclic prefix and frequency domain equalization. Shown in this figure, when it's in stress wave communication, the impact of reverberation and the dispersion can be alleviated by the OFDM. We show the overall system configuration in this page. We choose 200 to 230 kilohertz to test the performance, and we also deactivate the subcarriers with long delay spread. These OFDM parameters are shown in the bottom left table, and at last, we use the 3 volts maximum driving voltage to limit the power for underwater nodes. In the next section, let's go through the performance evaluation. We first analyze the performance of point-to-point pipe communication. Notice that the stress wave channel is spatial correlated. Utilizing a receiver array is aimed to increase the signal-to-noise ratio S than R. In other words, we don't expect this array can increase the multiplexing gain. 3 steps are shown in this pipe communication scenario. We first estimate the subchannel using OFDM channel estimation. It is shown in the right figure. Training sequence is transmitted before informative symbols. Since the reverberating stress wave channel is a time-invariant channel, once the channel is estimated, the transceiver can memorize the channel for successive data transmission. And in the step 2, based on the estimated channel, a single input multiple output combiner can be derived. In this work, we use the maximum ratio combining, MRC, to test the result. As known to all, MRC increases the signal-to-noise ratio by summing up every individual SNR. In this figure, you can see the cumulative distribution function shows a nearly 5 decibels SNR gain comparing to the average signal-to-noise ratio. No further channel estimation is required if the transmitter is known by the receiver. So in the step 3, we want to reuse the combiner for the upcoming transmission. Finally, calculate the spectral efficiency of this 1/3 SIMO as 1.18 bits per second per hertz. In another application, we consider the multiple sensor data acquisition problem. In this scenario, a cluster head wants to collect and process the data from non-pipe sensors. FDMA means a single carrier frequency division multiplexing access. It has a low peak to average power ratio and is more attractive than FDMA in the uplink. The goal is to maximize the rate sum capacity of the FDMA. Again, due to the time invariance, we assume that each sensor's channel information are fully estimated. A channel-dependent scheduling is to maximize the rate sum capacity based on this channel static information. It can be shown in this equation. The sigma represents user case SNR on the subcarrier I. At each subcarrier, the SNR of all the users are compared, and the user with the biggest signal-to-noise ratio will have this subchannel. The scheduling process is illustrated in the right figure, where the different color represents 3 users. Subcarriers are assigned to the user whose channel response is the largest. Finally, our result shows that the FDMA rate sum capacity can be at most 75.18 kilobits per second, with this 30 kilohertz bandwidth and 3 volts maximum voltage constraint. We characterize the reverberating stress wave channel as a time invariant, spatial correlated with non-flat frequency response from the model analysis, concept simulation, and experiments. We also use the OFDM to implement the multi-carrier stress wave communication and channel estimation. At last, we evaluate the channel capacity in 2 scenarios, the point-to-point communication and the distributed sensor data aggregation, with a maximum driving voltage constraint. Here is the acknowledgement. Our work is supported by the NSF, and here is the potential conflict of interests. That's all. Thanks for listening.